Setting up a GenDug is done basically with a file like this. This is a simple one where you can't act any of the consensus rules, defaults to like a basic proof of work chain. The Dug entry, just under the address, is where you would put an actual contract that holds the code for Dug. In this case, there is none. And you can set a bunch
Excuse me, Ethan?
a few other parameters.
Are we supposed to watch something?
Global parameters. Yeah.
Ethan, we haven't seen your screen yet.
I was hoping. Oh, sorry.
Yeah, if you could just roll back a little bit.
Yeah, I figured you could pull up like the Thelonious I/O.
Oh, hold on.
Okay, let me see if I can screen this.
It's OUS.
I'm sorry?
There is a screen share button to
IOUS.
the left.
I think he's going to share his screen, Rob.
Although I don't know why it became so small for me.
There we go, screen share.
Right. Yeah, this is not the best format, obviously, and we apologize for that. Oh, it seems to be working. So if you click on Ethan now in the Hangout, there will be a green arrow and you should be able to see his screencast.
I think we have to click the green arrow.
Oh, I get to click it.
Cool. Is this visible, or how do you guys do it with this?
Yeah. Yeah. Yes.
Yep.
Cool.
I'll put you back on mute.
Okay. Cool. Okay. Yes. So as I was blabbling on about before, this is our configuration for a blockchain. This is like the default one that's run when you install our tools and go for it. Oh, sorry, no, it's not. This is a more advanced one. This is the default one. Okay. So as I was saying, this is Dug, is the address of the Dug contract. If you want to see what getting GenDug looks like, I could actually do that. Sorry, I have all kinds of crap going on. So look here, 1.5. So for configuration contract or thing up, and that was getting GenDug. It's like 15,000 lines of virtual machine execution. It's kind of terrible to debug, but that's what the EVM looks like for you. So in our most basic one, there is no GenDugging. We don't even use anything at the heart of the chain. We just set some basic parameters and go for it. This now is more akin to the one I was actually just deploying, where we have some contract that has actually all the code that executes in the GenDug contract. So this is written in LLL, sort of an older Ethereum contract writing language that's very low level. Basically, our chains are tracked by chain IDs. So after the Genesis Dug is launched and the Genesis block is all created, we take the hash of the Genesis block. And that's the chain ID, but really what we'd like to be doing is have chain IDs signed by individual developers, so that if two different developers want to use the same chain, the same sort of Genesis block, but have them actually act as different chains, they can sign them with different private keys set up, and thus set up new chain IDs. And so basically, once we have sort of this bigger ecosystem, this multi-chain ecosystem, you'll be able to find a chain by a chain ID. You know, you'll look it up in some DHT and it'll tell you where the peers are for that chain, and then you can go and connect into that chain and sync up with it. So setting the private key allows you to as the dApp developer, to sort of provide authentication over the chain ID. If you don't want to provide that, but you still want a unique chain, a unique ID, you just change unique to true, and then you can have multiple different chains that all have the same Genesis block, but with different chain IDs. So that's just a little convenience. So then, in the ways GenDug can run, for historical reasons, we've sort of had different models. Some have been for testing. The main one now is the virtual machine model, where everything sort of actually runs through contracts in the VM. So this tutorial is a little bit old, actually. I wonder if I have one below. No. And so nowadays, that model should always be set to VM. And yeah, so it basically decides on what kind of consensus rules are followed, and they're probably scripts that run in the virtual machine. Whereas if you set the model to yes, everything would get validated. If you set it to no, nothing would, and so on. Those are useful for testing. You can also turn your GenDug off by setting no GenDug to true. Consensus is sort of irrelevant now. You can set the difficulty of the blocks. It's actually 2 to this number. So if you want your blocks to come a lot faster for the sake of developing, bring this 15 down to a 5 or something, and your blocks will be super fast. And then these 3 guys, these public, mine, create, and transact, are sort of the main permissions for determining who can do what on this chain. So by setting these to 0 or 1, you determine whether everyone is allowed to do this activity. So in this case, this is not a publicly mineable blockchain, but it is anyone's allowed to create transactions and to create contracts. That's these 2 ones. So assuming this was 0, no one, or given that this is 0, no one's allowed to mine, but further on down, we specify some specific addresses, in this case only 1, and the permission for that address to mine is set to 1. So this BBBD address, who's given the name of the one and only, is the only person basically in the world who's allowed to mine on this blockchain, whereas anyone's allowed to transact or create. And so if you try to mine a block by disabling something in your client to make it go through, everyone will check when they receive that block who the Coinbase on the block, and thus they'll go. And of course, the blocks have to be signed by the Coinbase, and so everyone will check. Oh, this is not a publicly mineable blockchain, and then they'll go look at the list of valid miners in the Genesis DUG, and they'll check if the Coinbase is this BBBD or not. And since it's probably not, they'll reject the block. And same thing for creating contracts and for actually transacting. So that's like the basic sort of mission level overview. There's a couple more parameters. The max gas per transaction, that's basically set at infinite for now, but this is how we can avoid the halting problem with the Turing complete virtual machine without having to charge for gas. So Ethereum's model, because it's a big bad public blockchain where real cryptoeconomic principles are in play, you got to say, okay, we got to charge everyone per step of execution, and then they cap the amount of execution in a block. Whereas what we're doing here is saying, okay, we don't want anyone to have any ETH or anything like this to actually do anything, so you're allowed to transact for free, but there's a max amount of gas that you can use in a given transaction. And from the perspective of a developer, say, who's the only person allowed to mine and who's hosting this thing, that's reasonable, and we assume that the profit comes from the usefulness of the application rather than from getting paid for the actual execution steps like you would in a public blockchain or in a publicly mineable blockchain, say. Yeah, and so that's basically it for the Genesis.jsons. Here's one with some more built-in addresses with different tools. And then here we go. Here's a, oh, sorry, there should be a better one down here. Okay. Here's what I was looking for. Okay, so as I was saying, we've more recently been moving as much as we can into the virtual machine, and so you set model to VM, and then you can use those contracts. You could use the defaults by setting sweet name here to default or to standard, or you can actually specify paths to contracts to handle the different sort of stages of a consensus mechanism. So right now we've broken that down into like 5 stages. Basically, you have You have code for verifying a block. You have code for verifying a transaction. You have code for just checking a general permission, so whether or not user X has permission to do Y. Then there's computing the difficulty, or what the difficulty should be for a given block. This is more of a proof of work based thing, but there are analogies in the proof of stake system. And then there's this compute participate, which is to determine whether or not you should bother mining or trying to commit new blocks. And so, if you had consensus rules such that the mining was a round robin, this is the contract that would run that would tell you whether it's your turn to go in the round robin, or if it was a proof of stake based system, this would be the contract that runs that tells you whether you should sign the blocks or not, whether you're valid, and so on. So just by setting up these contracts, you can now run a good deal of the consensus rules actually through the virtual machine and have them be updatable, and they could be voted on and so on at the protocol level, instead of through like some meta protocol thing where you have issues on GitHub and people try and figure out whether to push to master or something like this. Yeah, so that's basically, so this tutorial page, this is a ton of explanation. If you want to see what the block verify contract, the transaction verify contract actually looks like, this is the actual contract that's validating transactions. It's just a mess of LLL. Basically, the data comes in as a serialized transaction. We set up all the different points, the parts of the transaction, and then we go and deserialize using this RLP decode opcode that we added in. We're actually probably just going to write that in the Ethereum virtual machine itself, so you can use it as a contract instead of as an opcode. It's probably more general that way. And then it goes and checks that the transaction hash is valid and that the person has permission and so on. And yeah, that's basically that. Feel free to scroll through this tutorial at your own leisure if you think you missed something or you want to review it again. And yeah.
Yeah.
Oh shit.
Yeah, so that's the actual blockchain system that we use. When it comes to applications, the contract system, the smart contract backend is just part of an application. You will also have, as I pointed out before, and I'm going to put that up again and see if the screencast working a bit better this time. How does it look? Is it big now?
Yep.
Ethan, can you see?
Sorry. Yeah, the writing is still pretty small.
Okay. Let us see if I can. Is it better?
Yes.
Oh yeah, it's a little better.
Okay. Well, what Ethan was talking about here is the distributed data store module, and that is one part. Now, we're going to look at an extreme, but yeah, that's the blockchain part. And you also have, as Ethan mentioned, you also have a simple one too. So you could have a distributed file store, for example, which is what the example that uses alongside the Thelonious blockchain. And to coordinate these different modules, you write JavaScript. It's like Node, really. So the applications themselves, they look and feel pretty much like a normal application, except a normal Node application, except you call Thelonious and IPFS or some other distributed file store instead of, I don't know, an SQL database or something. So that's the scripting layer, and then you have the UI, which is just the regular HTML, CSS, JavaScript web page, essentially. So I'm going to go into our little example application here. This is an actual running application, and the files that we have in here is see there's a comment there, I'm just gonna see what that looks like. Okay. So what you have here is, first of all, the package.json, which is a simple file, looks like with Node, the name, the version, the home page, etc., and then the module dependencies, which is, in this case it's Monk, which is short for Thelonious. There's some data, the peer server address, the ID that Ethan talked about for this particular chain. The whole point here is that every dApp has their own chain. They don't just live on like a public Ethereum chain or something. Everyone has their own chain. The root contract, and then it also has a dependency for IPFS, which is the Interplanetary File System, a new distributed version of the peer-to-peer file store. This is a little bit of data that's needed for the server to be able to run the application essentially. And then you have the UI part, a simple index file, and this one in particular is just, as you can see here, we will look at it, it's a very simple UI. But a normal web page. There is JavaScript that comes with it, and then here we have the contracts, which is the contracts that are deployed when the chain is created. You can actually look at this. This is the very simple contract. It's an Ethereum contract. Would run just as well as on an Ethereum chain. The only thing it does is it takes two pieces of data. One is a hash from IPFS and one is a name. Yes. So we're not going to look at this contract, but yeah, this is a regular Ethereum contract or Thelonious contract. They're pretty much the same in most cases, and it's part of the dApp logic. It's part of the smart contract backend of the dApp, and then finally. So that's the UI and that's the contract. And what ties them together is the backend JavaScript, which we have here. And this is what happens when you make a request from the UI to store a file, for example. You want to store a file. This is what this application does. Or it gets a hash from IPFS, and then it writes into the Ethereum contract the name of the file and the hash of the file. So, which adds security to it, because you can look in the contract to see if I want to get the file. You use the name there, and then you get a hash, and you know that is the right file. So, and then so this I'm not going to get too much into this, but yeah, there is some simple JavaScript. This is the objects, an object form, I guess, has a handle, some custom-made routing here, but basically there are two functions. You can add a file or you can get a file. When you add a file, it will take the name and the data. It will turn the file name into a hex string instead, an ASCII file name turn into hex. It will write that file, the data, into IPFS, and it will get a hash back. And it will take the name and the hash, it will push that to the transaction data. It's just like an Ethereum contract. This is put into the TX data in the transaction that is sent to the, and then the commit here makes sure that this transaction is mined directly. So after this is done, we will have a file in IPFS that everyone has access to, and it's also there's also an entry in the contract that says okay, this file name has this particular hash. So when we get a file, it will take, we'll take the file name. It will look. This is how it gets it from the contract. It will get the hash from the contract this way. Then it will read file. This is another function. It takes the file from IPFS using the hash, that is the identifier, get the data that way, and then send it back to the UI. I'm going to launch this application now. Let's see here. I will do that. It's the way we distribute this is through Docker. You make Docker in essentially. Just started this application, and I'm just going to do something quick here. Let's see. Switch, and then should now run. Yeah, this is, and again, this is supposed to be very simple. This is an example for builders essentially. It's not to demonstrate the stack. It's a starting point for those who wants to build applications. So we can add a file here. Let's call it DDD. And then do this and submit. It will take some time for it because now it's mining some other stuff. There we can get it. And now I do this. I should be we'll get this data. I could change the screencast to the log. Maybe that wouldn't be very useful. I'm gonna change so. And instead show the console there to show what actually happened. Let's see. And this is almost done, by the way. Screencast. Pretty sure this is it. Yep. So there's a lot of logging here, but what happened here when I did all that stuff was first it would be here. Started HTTP hello world. It sent a regular HTTP request to this address here, this endpoint add, and then it used, you can see here, say IPFS says it stored that file. This is the base 58 hash that we've got. And then pushing stuff to Monk, which means that it took the hex version of the name of the file, and then also here is the hex version of this base 58 hash from IPFS. And then we can see it did a lot of stuff here. Got a hash, blah, blah, blah.
Andreas,
and then
we really can't. It's kind of hard. Can you zoom in?
Yeah. This is not, I was about to stop anyway. So the point being that